Okay, let's start. There's no microphone today, so I'm going to have to project. This is the most number of people we've had in weeks. What's going on? Is something canceled today? Usually the Fridays are really empty, so something's going on. I'm kind of curious what it is. So everyone wave to YouTube. All right. We're online. Okay, so we're going to have another fast lecture today. Guys, it's supposed to be sad. So we're getting near the end of the semester, and I'm trying to have less content as we get near the end. So today will be around another half hour or so. And I'm just going to round off some of the linear regression ideas. Right, by the way, regression very often, we talk about, when I'm looking for images for regression, I type in regression in the Google image search, I always get hypnosis images. So that doesn't help at all. Just so you know, regression, the word means a whole lot of things. I mentioned that biologically it has to do with biological characteristics like height regressing to a common mean, and in the psych zone it has to do with regressing backwards in time, previous experiences. That's kind of relevant to statistical regression, where you are regressing forwards in time based upon a mathematical model. Right, so what have we done so far? Last time we discovered the regression equation, where y prime is the predicted values of y based upon a model that we got from existing data that associates values of x with values of y. And we said that b is our slope, or regression coefficient, and alpha, or a, is the y-intercept. Okay. We mentioned that we're using the least squares method, which is all about vertical closeness to a projected line. We also call this the ordinary least squares method, because we're going to see several different types of least squares method. If you recall, least squares means that the distance from each point to the line squared, when summed together, we want the least possible value. So the line for which all of the points are the closest to it, if possible. Right? Which means that an outlier is going to draw our line up there in order to minimize the distance from that point to the line. And that can screw us up. So the last thing we looked at last time was Anscombe's quartet, which again I don't need you to memorize. But Anscombe's quartet was those 4 data sets that each gave us the same regression line, but they're entirely different data sets, because their different outlier values were such that they were pulling and contorting the line in different directions. So here are the other kinds of models that maybe you'd be curious about. This is the one that we use, the ordinary squares model, where we're projecting a line that goes through some point on the y-axis, and the distances from each point of that line are defined by a verticality. So that distance is parallel to the y-axis. There are other ways to do it. You could have done it modeling a line through the origin. That's sometimes done for reasons that I don't fully understand, but the assumption is predictions of 0 end up with outcomes of 0. The same kind of method. Or we could use an orthogonal technique. That's where the distance from each point of the line is actually a right angle to the line, which makes more sense intuitively, because distance tends to be orthogonal, not vertical. We could use that way with a y-intercept or through the origin. All different kinds of ways of doing it. We could do it distance via x-intercept as well. But we use this way. So an ordinary least squares method for which the distance is vertical, parallel to the y-axis, and the line intercepts the y-axis at a point, not necessarily at the origin. So here's another example. We have some hypothetical data. This is based on 100 middle-aged, older European men, and we're trying to find a relationship between some kind of cognitive function called the digit symbol substitution test, or DSST, and vitamin D intake. So can we predict, for example, your cognitive function based upon how much vitamin D you have? So first thing we do is we plot our individual variables to see how they're distributed. In this case, the vitamin D intake is somewhat normal, right? So it satisfies one of our assumptions of correlation, which is the data is somewhat normally distributed. The distribution of the cognitive test is also kind of normal, so that satisfies that assumption. We do our scatter plot, and we see, oh look, there's no relationship, right, in this particular test. You can say there's no relationship. Could you plot a line, though? Could you do a regression and get a line out of this? You could. You could run through the process and get a line. How would that line look? I don't know. Maybe in your imagination you can imagine it, but what we're going to see now is the second you plot a line, suddenly your brain does weird things. You see a relationship where maybe there isn't one. So just because you can plot a line doesn't mean there's necessarily a relationship. So today we're going to look at one way of testing statistically if that relationship is real or not. So here's another data set using the same relationship. Here we see something resembling a weakish relationship. Again, your mind starts to draw a line over here. Or you could say there's nothing going on. So if you can imagine trying to program artificial intelligence, a computer, to look at this and say, is there something going on here? Visually, we as organic beings would say, probably not. But an AI would have to compute some kind of relationship, usually a linear one, and probably say, yes, something's going on here as well. So now we kind of go into the realm of artificial intelligence a bit to figure out how much of this is forced meaning, how much of this is real measured meaning, and how much of this is kind of intuitive human concept. Here is something, a weak or moderate relationship. Again, same data, looking at relationship between vitamin D and cognitive function. But here we have, this was the weak, this is a little stronger. Here we have even stronger. If I took out this guy here, would it be as strong? It wouldn't, right? So that outlier, in many ways, is forcing our mind to think about a straight line. If that wasn't there, you see a blob. So very often, 1 point can make all the difference. Right? So go back to our very first data set. If I were to plot a regression for that first data set, I actually get this. I get a straight line that's parallel to the x-axis. Is that a relationship of some kind? No, not really. Any value of x I plug in, I'm going to get the same value of y. It's not a useful model. So we start to conclude that maybe whenever our straight line is parallel to the x-axis, i.e. has no slope, there's no relationship going on. So if I was going to do an hypothesis test to say whether or not my linear regression is significant or not, what do you think the null hypothesis would be based upon this observation? Yes.
That the slope will be 0?
Exactly, the slope is 0. So our null hypothesis is that the slope is 0. If the slope is 0, nothing's going on. If the slope is not 0, possibly something's going on. That's the assumption here. By the way, this is the equation for this regression, and it's saying that our predicted y value, don't worry about that function, is 28 plus blah, 0. Our slope is 0, so it's always going to be 28. Y is 28. Now, our next data set, we have a slightly higher slope. And our regression equation here is 26 plus 0.5 times vitamin D intake. So again, the way you interpret this is, for every measurement of vitamin D intake, I plug into this equation, and I can get a predicted cognitive function score. So I know that in my next set of studies, I can predict how this individual is likely to do on the cognitive test based upon how much vitamin D he or she took. Now, again, the line is a bit deceptive. Without that line, you might not see a relationship. Suddenly with this line, you're saying, oh, there's something going on here. But maybe there isn't. So again, we have to test to see if that slope is statistically different from 0. Doing the same methods we've used in the past. Computing a statistical test, looking up in the back of the book and seeing which one's bigger. Right? And here we have, again, our third data set. Slope is getting higher, right, as we get a stronger data set, and so forth. Right? Now, technically, our linear model looks like this. We have y equals a plus bx plus something else. Okay, what is that something else? It's an error term. So the error term, first of all, is not a constant. It's not going to be a number. It's going to be different for every value of x and y. So this error term accounts for something else. What does it account for? Let's say that, again, we're predicting, let's say it's your final mark. So y prime will be the mark in your final exam, and the x will be how you did in your midterm. So I'm trying to predict how you will do in your final based upon how you did in your midterm. I used last year's data to create a sentence for this, and I'm going to get an approximation for how well you do. But that approximation will not be precise. There's going to be an error associated with it. What do you think this error accounts for? Keep in mind, I'm only using your midterm mark to predict your final. What else could predict your final? When you write your final, is it just how you did your midterm that determines how well you do? What else determines how well you do? Yeah?
If you went to class.
If you went to class, what else?
Studied.
If you studied, maybe how smart you are, maybe how much sleep you had, all this other stuff. Endless numbers of variables. So all of that is conceptualized within the error. And for each individual, all those factors are going to be a little bit different. So the error measurement is going to be different for each point. So it's not a constant, it's not a simple number. When we do multiple regression next week, you'll see that we expand that error to actually try to measure those individual other variables, like how much sleep you got, like whether or not you studied, like how smart you are, like how old you are, all those other things. Right? But right now, all we say is there's an error. Right? So the effective variables that were omitted from the equation. What was omitted? Everything else. Maybe your gender matters. Maybe your race matters. I don't know. Maybe what your major matters. All these things are possible. In fact, in reality, everything else in the universe is encapsulated within the error measure. Obviously, some variables are more important than others. Well, your race is not as important as how well you studied. Whether or not you have a hat is not as important as whether or not you slept. Right? It may have a very small, minuscule effect based on your comfort or something. But in reality, everything matters. Some things matter more. So with multiple regression, that will be next week, we found a way to weight which of these variables matter more. And very often in real-life studies, we do these kinds of regressions to figure out which are the factors that are most predictive of the outcome. When I did this simple regression here, I assumed your midterm mark was most predictive of the outcome. I could be wrong. It could be how much sleep you had is most predictive of the outcome. It could be how smart you are is most predictive of the outcome. I made an assumption here. That's when the human component comes in and maybe screws up a bit. So right now we're talking about the error. The error, again, encapsulates all these other variables that we didn't know about. We also call this error a residual because it's what's left over after we accounted for the midterm mark. We write the residual as epsilon, and the book writes it as an e because the book is boring. But keep in mind, it's meant to be an epsilon. We've got our epsilons. We have our alpha, our beta, our epsilon, in the book's case, A, B, and E. Now, I is going to be the individual point. So let's say in the model I'm making, let's say I'm predicting your final mark based upon your midterm mark, and I'm using last year's data. So each of these i's is going to be each student from last year. So student 1, student 2, student 3. So the error for student 1 is going to be the actual final mark that student 1 got minus the predicted final mark that student 1 got. And the error for student 2 is going to be the actual mark that student 2 got minus the predicted mark that student 2 got. Obviously, the smaller the error, the more likely my sentence, my model, accurately predicts your final exam. I want to keep that as low as possible. If it's 0, that means my model is perfect. In fact, using your midterm mark is all I need to predict final marks. I don't need to know your gender, your age, your major, how much sleep you got if the error is 0. But it's not going to be 0. It's never 0. Right? So again, each one is going to be different for each individual in my data set. That's why it's not a constant. Now let's go back to the example from last time. Last time we tried to predict your final mark based upon your midterm, and we figured out that your final mark is going to be 1.5 plus 0.9 times the midterm mark, based upon last year's class experience. Okay, so if I put this in my spreadsheet, here is each student, 1 to 10, here is the midterm mark, here's the final mark, and using that model I just created here, I can fill in what the predicted mark should be. And I get these. So they actually got 3, but I predicted 3.3. This guy actually got 7, but I predicted 6.9. It's close, it's not precise. The difference is the epsilon. These are the differences. So in some cases, I've under-predicted. In other cases, I've over-predicted. In general, those are pretty small errors. You'll agree. Right? And again, each of these errors represents the other factors I'm not taking account of, like did you study, did you sleep, etc. If I square these, and why do I square them? Again, I square them to take away the minus sign. I get these numbers, and I add them all up. So this is the sum of all the errors in my data set. When we do the ordinary least squares method to make our line, what we're actually doing is we're keeping this as low as possible. So what the technique does, it runs through all the possible lines that you could produce and finds a line with the smallest sum of epsilons. In other words, it's the model that maximizes the influence of the variable you care about, in this case, your midterm mark. Pretty clear, right? Pretty elegant, actually. I like this explanation. It's quite elegant. So Again, the least squares method that uses a criterion for solving for A and B such that epsilon is minimized, and we call this the ordinary least squares method. Okay. Now, we have this thing called the standard error of the estimate. Remember, we have the standard error of the mean and the standard error of the difference, all that stuff. It's the same idea. In this case, it's if I were to take 1 billion samples and run the same regression, how many times would I get the same result? That kind of thing. So the larger the correlation coefficient between the two variables we care about, in this case, the midterm exam and the final exam, the smaller the standard error of the estimate is. The standard error of the estimate is an index and a measurement of how wrong the model is. In other words, how big epsilon is. Bigger epsilon, the bigger standard error. The smaller epsilon, the smaller the standard error. Standard error is given by this formula. This is the parameter. Again, the parameter estimate is in all possible stats classes, writing midterm 1 billion times. The relationship between that and the final will give me a standard error of this. Right? So that's the parameter estimate. It's given by the sum of all the epsilon squared divided by all the people in the sample under the root sign. Now, that's the parameter. The statistic is given by this. So again, parameter, statistic. The difference is the denominator. In the statistic, it's n minus 2, and the parameter is n. Obviously, because we're giving samples here, we're dealing with samples of a given class, we're going to deal with this formula, because that's the one that we can deal with. Now remember, that's going to be epsilon squared, and that's n minus 2. So that's our statistic. When we divide our sum of epsilon squared over n minus 2, that's actually called the mean square error. So in other words, this is the standard error, and if I square it, that's the mean square error. Under the root sign, not under the root sign. Under the root sign, not under the root sign. That's the distinction here. The mean square error. Okay, what do we do with that? So here we have all our stuff, all our data from last time. I compute the standard error of the estimate by plugging all this in and divide it by n minus 2 under this root sign, and I got 0.81. You can do that on your own. I trust you can do the math. Now we're going to do my significance test. Again, the null hypothesis, trying to figure out if my slope is 0 or not, or if my relationship is real or not, is that my slope is 0. The null states that my slope is 0. Because if the slope is 0, there is no relationship. So I'm going to test now, is the slope 0 or not? The alternative is the slope is not 0. I don't care if it's bigger than 0 or less than 0. All I care is that it's not 0. What do? I use a t-test for this. And the t-test here is going to be the slope that I compute divided by the standard error that I just computed as well. The degrees of freedom is going to be n minus 2. Right? Straightforward stuff. And what do I do once I compute the t? Can you guess? You can guess. You can do it. What do I do? You're smiling at me. You know what it is? No? Like everything else we do in this class, once I compute my statistic, what do I do with it? I'll look it up in the back of the book. Right? There's some repetition going on here. So, from our example, we have that was our sentence that we created from a model. We state our null hypothesis, the slope is 0. We compute the t, so it's going to be the slope divided by the standard error. So 0.9 divided by 0.81, we get 1.11. Degrees of freedom, 10 minus 2. And I look up in the back of the book. So in the back of the book, it says the t should be 2.31. We got 1.11. The book is bigger than our number, therefore we fail to reject the null and conclude 1. Yes? And that's what?
There's no relationship.
There's no relationship, exactly. Now, this is nonsense. Now, we do this because this is like standard classical statistics. Clearly, there is a relationship going on here. Hypothesis testing for regressions like this is pretty much never done because it doesn't really give a whole lot of information. But I present it to you because this is what classic stats asks us to do. So we're saying that statistically the slope is still probably the same as 0. However, our correlation coefficient is actually quite high. I would argue that there is a strong relationship between your midterm and your final, given our model we just created. So what do? No idea, okay? Except that in practice we pretty much ignore this. But I present it to you as something that you need to know because it's in the textbook. Okay. Now, there is a relationship between our linear regression and the Pearson's correlation coefficient. Remember, Pearson's and Spearman's are different. What's the difference between Pearson's correlation coefficient and Spearman's? Who remembers? Yes.
Pearson's is for interval ratio data and Spearman's is rank.
That is correct. Spearman's is ranked data, and Pearson's is not ranked data. So in our unranked data, we're looking at linearity. In the ranked data, we're looking at what kind of relationship? Remember the name for it? As one goes up, the other goes up. It's not a straight line, it's something else. Yeah, it's mono something. Monotonic. Monotonic. So monotonic relationship, not a straight line necessarily, but it goes up, right? So a ranked correlation coefficient doesn't care about the straight line, it cares about monotonicity. The unranked cares about a straight line. So it makes sense if I'm modeling a straight line that the unranked correlation coefficient plays a role because it's all about linearity as well. What was my third measurement of correlation? You remember that one's called? The one we need compute in class? You remember it? You're going to have to remember this eventually. See, this is a problem with cheat sheets. I discourage you from knowing things. Kendall's tau. Don't forget Kendall's tau. That's the third one. Okay, so this is the relationship between the correlation coefficient and the straight line equation. So this is kind of intimidating. Don't worry about it because it gets easier. So here we have the deviation scores, which is our epsilon scores, and the relationship between the standard error and the r squared is kind of like that. If I simplify this, it comes down to this. Our correlation coefficient is essentially 1 minus the sum of all the square epsilons divided by the sum of all the deviation scores. Given this relationship, if I give you a straight line equation, you can compute what the correlation coefficient is. If I give you the correlation coefficient, you can compute what the straight line equation probably is. You can go back and forth between the two because they're saying exactly the same thing. So in the example we just did, our correlation, r squared at least, is going to be 1 minus the sum of all the epsilons over the sum of all the deviations, and I get 0.91. So r squared is 0.91, r is going to be the square root of that. Do you remember what r squared means back from the first half of the class? R squared gives us a certain measurement. That's useful, yeah? Yes, it's the percentage of variance accounted for in one variable by the other. Now, you had asked before, how is that possible? I didn't really give you an answer back then. It's possible because of that epsilon factor. We're talking about within the deviation scores between the predicted values and unpredicted values, that's how much play there is. So the missing part is essentially the epsilon. That's how it's possible. So if I were to take the square root of that, I get 0.955. Is that correct? Let's go to SPSS and figure it out. It's true. SPSS gives me the same answer. So the work I did by hand gives me the same answer that the computer gives me, which makes me very happy. That's great. Okay. As I mentioned, the squared residuals are what is left to be explained. That's the r squared minus 1, really. When we do multiple regression, this is going to get a slightly more complicated because a multiple regression r squared is a different kind of r squared. It's an r squared that accounts for the role of multiple variables. So right now we've done a sentence, a model, which you predict your final mark based upon one factor, your midterm mark. And the r squared shows how much variance in the final model is explained by the variance in the midterm mark. If I were to add another variable, let's say how much sleep you got as a percentage, 8 hours, 9 hours, whatever it is, suddenly my equation got more complicated, and now my r squared is more complicated. The r squared now says how much variation in the final mark is explained by both of these things. If I add a third variable, like how much you studied, right, the r squared now says how much variation in my final mark is explained by all three of these things. Each time I add one, my r squared goes up less and less and less. It's a law of diminishing returns. That's why it's not advantageous to throw in everything I know. Just throw in the ones that I really think are going to be predictive of the outcome, because I'm not gaining all that much predictive value at the end of the day. We'll see that when we look at it next time. So the lesson there, I think, is that this is all kind of mechanical and automatic. We put some numbers in, crank it out, and get a number. But the human intelligence and creativity always plays a role of figuring out which variables I put in what order, and which ones I care about, and how to interpret the results. We looked at hypothesis testing for where the slope is equal to 0, but I said it doesn't really matter. It's the r squared that matters. We have a very high r squared there, 0.91. 91% of the variance in the final is explained by the midterm, and yet we say the slope is equal to 0. That makes no sense. I say ignore the slope aspect. Focus on the r squared. If you do this in SPSS, you can use this and get the outcome like this. So note that when SPSS computes R squared, it gets a slightly different value because it's using a slightly different technique. And it looks at, well, you can compute 95% confidence intervals as well if you want, and so forth. All right, quick and dirty lecture, and you're free. We're almost done. Like 2 lectures left or something. We're almost done. You can do it. That was like, what, 20 minutes? Right on.